Routh-Hurwitz, basically, that criteria was developed way back in 1905. So it tells us, like, how many poles are in the left half plane, how many poles are in the right half plane, or how many poles are along the JW axis. Okay. If you have a given system, it may have a certain number of poles. All right. So one thing is that if you know like how many poles are on the left half plane or right half plane or along the J axis, what does it ultimately tells you that whether your system is stable or unstable or marginally stable. All right. So this is a criteria to determine the stability of your system. All right. So so how actually what this criteria is or how it works actually. First, like we have to create or generate a table which we call the Routh table, which we will discuss later on now. And secondly, once you have created or generated a Routh table, then you interpret that, you understand that, or you take the meanings out of that, that what does this table tell us. Okay. So there are two steps to it. Like first is to generate the table, which is called the Routh table, and secondly to interpret that table. All right. So that's what is called the Routh-Hurwitz criteria. Again, like the purpose of it is to determine the stability of your system, and it tells you like how many poles are on the left half plane, how many poles are on the right half plane, and how many poles are on along the JW axis. Okay. So one question that might comes into your mind that if just the poles or the position of the poles is what like determines the stability or instability of the system. So like there are the calculators there, or there are computer programs there, like they can easily tell or calculate the roots of any given polynomial, right? So why we are still using the Routh-Hurwitz criteria? The thing is that like it not only just tells you that the stability or the position of the poles, but like it also gives you the region of stability. Once you go into the design part of your course, you are interested in that. For example, if your system is unstable, all right, it may not be unstable for all range of values. Okay, it may be stable for certain values and may be unstable for certain values. All right. So if you know that what is the region of stability, okay, and your pole, for example, is lying out of that, so in the design part you want to bring that pole back into this region of stability. Okay. So that's where actually Routh-Hurwitz criteria, it tells you what are those regions of stability and instability are there. Okay. So that's why it's so much important to understand. So we have an example there in the end. So that would be actually helpful for us to um, understand the importance of the Routh-Hurwitz criteria. Okay. Just consider an equivalent closed loop transfer function of in a figure. Okay. For example, we have any general system, and the closed loop transfer function, you can see here, like RFS is the input or CFS is the output, and the equivalent closed loop transfer function is what like NFS is something in the denominator, in the numerator. We are not interested in that. What we are interested in the denominator. Okay. So in the denominator, actually, we just write a polynomial. Let's say it's of degree 4. Okay. So the highest power of S is 4, S cube, S2, S and S naught. Okay. And A1, A2, A0, A1, A2, A3, and A4, these are basically your coefficients that they associated with those S values. Okay. That's a general way of writing, for example, a polynomial of degree 4. All right. So we have this one. So now, like, how you create the Routh table for it. All right. So the first thing is that just look for the highest degree. What is the highest degree here? It's basically 4. Okay. The highest power of S that we will look for. Okay. So S4, you start from S4, come down like S3, S2, S1, and S0. You keep on coming down like that until you reach S0. Okay. That's the first column that you always do. Like, just look for the highest degree in the denominator and start from that, go all the way down to S0. All right. Then you have to fill these rows. Okay. The first row, always look for the coefficients. What are the coefficients associated with it? So for the S4, what is the coefficient over there? It's A4. Okay. You write A4 in the first row. Okay. For SQ, what is the coefficient there? It's A3. All right. You write it here. Then here on the upper side is S2. Basically S4, then alternate values of or even values you write on one side. S4, S2, S0, S3, S1, and this value will be 0 because it's going on the other side. Okay, so your coefficients will be A4, A2, and A0. A4 is the coefficient for S4, A2 is the coefficient for S2, and A0 is the coefficient for S0. Okay, for the even values. For the odd values over here, A3 is the coefficient for SQ, A1 is the coefficient for S1, and you don't have any coefficient over here, you just write 0. Did you understand like how for SQ, what is the coefficient there? It's A3. All right, you write it here. Then here on the upper side is S2. Basically S4, then alternate values of or even values you write on one side. S4, S2, S0, S3, S1, and this value will be 0 because it's going on the other side. Okay, so your coefficients will be A4, A2, and A0. A4 is the coefficient for S4, A2 is the coefficient for S2, and A0 is the coefficient for S0. Okay, for the even values. For the odd values over here, A3 is the coefficient for SQ, A1 is the coefficient for S1, and you don't have any coefficient over here, you just write 0. Did you understand like so? That's the first step in creating the Routh table. Again, you just look for the highest value of S, start from there all the way down to S0. Then the first two rows you create them from the denominator polynomial. Okay, like in this case as A4, A2, and A0, and A3 and A1, you just take these values from the polynomial. Okay, if any term, for example, here is missing, you can just put 0 over there or whatever it is. Going next, you see here again for the same S4 down to S0, and then these A4, A2, A0, A3, A1, and A0. This is what you have already defined previously. Now for the rest of the Routh table, how you take on the values. So here is the formula. Okay, the value just underneath that, it will be with this minus sign. Then you take the determinant of A4, A3, what is immediately above it, and the next one, A2, A1, divided by A3, this coefficient. Okay, the second one will be again this with minus sign, A4, A3, this first column, and then this the alternate column, A0 and A0. Okay, and after that, like for this value, okay, again this is A4, A3. Okay, but the next one is obviously 0, 0. You take this column as 0, 0. Okay, divided by A3. This is the formula. Okay, once you solve it, you will get certain value. You call it B1, this is B2, and this will obviously 0 because this whole column is 0. When you take the determinant, this whole thing will become 0. Okay, now once you have put the values in the third row, you go to the fourth row. Again for the fourth row, what would be it? It would be determinant with minus sign. The value, whatever value comes over here, B1, and whatever values come over B2. All right, so you do like that. So A3, so you consider the immediate above two rows for that. So here it's A3 and B1, and A1 and B2, whatever values, minus sign, divided by whatever the coefficient or whatever the value here is there, it is divided by that for all of these cases. Okay, then second one is again A3, B1, and what's the value over here? It's 0. Okay, 0, 0, 0, 0 comes there. Obviously the next after the values on the right side, they're all are 0. Okay, then again for the S0, you have the C1. So this B1 C1 value, then this B2, and this value is 0. You can put it 0. Then again B1 C1, and these values are already 0, so you can put 0, 0 there. Right? So in this way, you will come down, and by S0 you just get a single value there. All right. Once an example will come, so you will get a better idea.